slide. In case someone has missed, I just wanted to give a quick overview. On today's handout, you'll find some of the descriptions of the processes that I didn't include in the first handout, so you can go back and see there's a little bit of a description of nucleosynthesis and solar system formation, just some brief notes. After I leave here today, I'm going to upload the slides from the PowerPoint presentations to my own website, and I'll figure out how to distribute that link to everyone, either email it out or, worst case, you'll get it on your handout next week with the URL so that you can look at the PowerPoint presentations. And then today is really the last of the lectures that I'm going to go where we're talking about events that happened prior to a real geologic record on this planet. So this is the last of the sort of theoretical lectures, in a sense, where we have to infer a process that took place prior to us getting some of the first crystalline material, which we'll come to learn as our zircons that are up to about 4.3, 4.4 billion years old. So this is, we're going to finish with we're going to go through and spend most of the lecture on something called the magma ocean. And the magma ocean idea is that the planet was entirely molten, and that this outer molten portion is called a magma ocean. Sort of like if you've seen images of the lava lakes on volcanoes, that's the picture that you should have in your head. And that this is a really nice description of what the planet looked like, sort of shortly after the moon forming event, shortly after, during the sort of the core formation in this really early time. The question is really, what did the planet look like as that magma ocean cooled? What did the crust look like? That's one of the key questions that I want to get to and get into to not give away the punchline. How really little we know because of how simply complicated these models are, that there's a lot of unexplored area. So we don't. The punchline to this is we think a process like this happened, but we're not entirely sure what it left the planet with. So starting from next week, we're going to try to look at the geologic record to see how we can understand this. So just to sort of remind everyone, the point of this lecture series is really to try and give you the view of the early Earth if it was a sort of a hellish time period or something more pleasant. And really what this means is how quickly did this transition happen. Last week I talked about the moon-forming impact, where you're slamming a giant object into the Earth, and you're putting some part of the Earth into orbit. You're making a silicate vapor, and when that recondenses and sort of reforms, you're going to have something like this. And then the question is basically how quickly did this transition into something with water and an atmosphere and a more pleasant environment. So we started off with looking at the nucleosynthesis. The nucleosynthetic processes, where on the vertical scale, these are the different elements. So starting at the atomic number, here's the number of protons, and then here's the number of neutrons. So you can see in red here is the S process path. So this is if you're adding neutrons very slowly, then you can sort of make your way up. And there's the R process, which just adds a ton of neutrons basically all at once, and then stuff has to decay back to the stable region. So this gives us, the reason I wanted to go back to this gives us a lot of isotopic variation that's going to become increasingly important as these lectures go on to try and understand these processes. So this is really, the baseline here is that there's a lot of variability in what's happening. So again, these are different elements here, and then here you have the different isotopes that are shown. So we can kind of go up the S process, and what you can see is that there are a lot of these sort of branching points, where here in nickel, it can either decay up and go to zinc, or it can go on and then make a stable copper isotope rather than making, in the decay, an unstable copper isotope. So you can start to get a lot of variability. The R process is going to introduce a lot of variability. This is sort of happening. You want to think something like supernovas when you're thinking R process. And this is going to leave the solar system materials with a lot of different isotopes of the different elements, and that these are going to have different abundances in the different meteorite classes and different behavior. We're going to look at some of the ingrowth. So here's rubidium. This is 85 and 87. 87 is going to radioactively decay to strontium 87. We're going to make excellent use of this system. It's one of the more important geologic systems. So just to sort of give you this reminder that it's really this inherent complexity in this process that's going to allow us to trace and answer some of these questions. And it's also this that, for example, allowed us to use both the hafnium tungsten and the lutetium hafnium systems in the last lecture to try and understand something about when the Earth got a core and how old the Moon is. We're going to see the lutetium hafnium system quite a bit more in a terrestrial context about when crust formed. So if you have some questions with that, we're going to go back to it. The solar system, just to sort of very briefly sort of give to catch anyone up who wasn't here for the first sort of parts of the lectures. How did we get it? There was a sort of a giant molecular cloud that had a lot of gas and dust. This material basically started to collect. It's polluted from supernovas popping up, from winds being ejected from stars. And so you're collecting a lot of material, especially from a lot of different stellar sources. Eventually, you get a lot of this stuff, and it's going to concentrate in the center, and either that'll be enough on its own, or there'll be some event that's going to trigger the collapse of this cloud into a rotating disk, where the inner part is quite hot, and it's going to make the star, and then there's basically a temperature gradient to out here where it's quite cold. The material in the sun is going to become, the material in the center is going to become the sun. It's going to fuse hydrogen. The disks, which I'm just putting this in because I still think this is one of the most impressive images that's been taken in recent years. This is such a protoplanetary disk imaged by ALMA. And so here you can see these gaps are planets accreting. And in the middle, you're condensing from a gas, so magnesium, silicon. The actually first things that are going to condense are calcium and aluminum-rich minerals that form the calcium-aluminum inclusions. This is how we know the age of the solar system. This is happening basically contemporaneously with the sun forming. So that's basically your start is when these calcium-aluminum inclusions formed. So again, in the middle, you're going to get the hot stuff, the silicates, and in the outer stuff, you're going to have the light elements, your hydrogen, your helium, your ice. And as these particles collide and stick together or break apart, they're going to grow up to planetesimals that are a few kilometers across. These are going to hit each other, and you're going to slowly grow larger and larger objects over a time scale of maybe 10 to 50 million years. So this is all happening in the blink of an eye, geologically, compared to the age of the planet. And then, as the protoplanets grow, so this is the zoomed-in ALMA image again, and this is about 1 AU, so this is about 1 Earth distance to the sun. So there you can see a planet forming really close to the star at about 1 Earth-Sun distance. So this could be an infant Earth that you're seeing there. So, for today's lecture, in order to understand magma oceans, we need to know quite a bit about how molten silicates, so how molten silicon, oxygen, magnesium, and iron behave at incredibly high temperatures and incredibly high pressures, things that are just not really that easy to make in the lab, and things that are going to have behaviors that are not quite what you're used to. So in order to do that, I wanted to back up and just try and give a little bit of an introduction to the thermodynamics, and in particular, what happens as things heat up and as you increase the pressure. And that, I think, will be very useful to try and give you perhaps not a taste for how this would have worked, but a taste for how simply difficult this problem is. And I have some images of the experimental apparatuses, and in fact, we're going to talk about shockwave, which is an artillery gun being fired at a rock. As the thermodynamics is happening, any system that you have, so if you have the water sitting here, or you have your, whatever you want to think of, let's just let's just pretend my water bottle is frozen, and it's a block of ice sitting here. It's too warm out in this room for ice, so that would be an unstable state. And so as it's getting warmer and warmer, it's trying to go into the stable state. So it's trying to meet the same temperature as the surrounding environment, and it's trying to basically find stability. So any thermodynamic system is going to want to go towards a stable place from an unstable place. So the rock is going to fall and roll down the hill, because that's the most stable location for the rock. You can also have metastable states where they are kind of in between. There's a little bit of a barrier, and the system might not have the energy to get over that barrier and into the more stable phase. One of the classic examples in minerals is diamond. Diamond is not the stable phase of carbon in this group. Diamond will try to revert to graphite, except that the potential energy barrier is so high that it can't get there and make that transition. So diamond, actually, as beautiful as it is, not a stable phase. It's a high pressure product of carbon. So it doesn't, that's why you can't form it at low pressures. So stable is when it's at rest in the lowest energy state in the system. Whatever we're talking about, whether we're talking about the water bottle or a little bit of silicate melt or the diamond, it's going to try and go into this lowest energy state. And metastable is the low energy perch. So, unfortunately, we can't go up and get a flag from the mineral telling us what its energy is and what energy it would like to have in its most stable state. Nature isn't that simple, so we need a way of accounting for this. And for this, people have come up with the Gibbs free energy. This is a way of accounting for the chemical energy of a substance. And this is really what the system is trying to minimize. They naturally want to minimize their Gibbs free energy. So if you have a pressure and temperature condition, if you have a phase, or if you have, say, the water bottle sitting in the room, ice is not the most stable, is not the lowest energy state, liquid water is. So it's going to undergo a phase transition from solid to liquid to try and minimize the energy. So the Gibbs free energy is related to the enthalpy minus the temperature times the entropy. Entropy you can think of in terms of randomness, but you can also think of it in terms of how many configurations there are for a system. How many different ways are there to arrange a system? So for example, if I have a quarter, and that quarter can be heads or tails, that would be an entropy of 2. As I start to add more and more quarters, each one can be heads or tails, and that has a lot more possible configurations. So the entropy then is a lot higher. So this is related to how many states are available, how many arrangements are there, and is not a term we're really going to put a number on. So basically, this is related to how much heat there is in the system minus the temperature times some configurational term. So we're always going to try and minimize this. And a phase, just to give, is anything, it's a mechanically separable portion of a liquid. We can separate solid from liquid. We can separate ice from water. We can separate vapor from liquid. We can separate vapor from a solid. And a reaction is just some change in the nature or type of phases in a system. So going from solid to liquid is a reaction. Going from having two chemicals that haven't yet reacted, forming together, bringing hydrogen and oxygen together to make water is a reaction. And they're always written in the form, and you'll see them, reactants are equal to products. So, how do we then do this? Well, if there's a change in some property, such as we have our reaction, I'll have an example in a second. Basically, the change in the Gibbs free energy is the sum of the Gibbs free energy of the products minus the reagents. So in this case, 2A plus 3B is equal to C plus 4D. This is going to be GC plus 4GD for the products term minus the sum for the reactants. So the thing is, G and H are not things that we can determine easily. We can determine the volume of the substance, right? The volume of the water in the water bottle is pretty easy. It actually tells me on the label, but we can go out and measure that. Temperature, really easy to measure. Pressure, really easy to measure, right? In this room, we're at 1 atmosphere. So those are easy, but we don't actually, these G and H are really just accounting things. They're really just a convenient way to track that it happens to work, that nature wants to minimize this quantity we've chosen to call G. So these are basically, for our purposes, this is an accounting thing. So the complication to this is that we can really only determine changes in this, since we don't have an absolute scale to reference this to. We can say, if I have ice and it's going to water, then the Gibbs free energy of the water is lower than that of the ice in our room. So we can learn something about a change in the Gibbs free energy. The delta H term you can measure by calorimetry. You can basically measure how much heat is given off as a reaction proceeds. So we can talk about melting. The classic example is that it takes so long to boil your water because you need some heat to overcome the gap into the vapor phase. And we arbitrarily are going to reference this basically to room temperature and room pressure. This is in megapascals. This would be 1 atmosphere. These units you're going to see GPA, which is gigapascal. So this is 1 million pascals of pressure. Gigapascals would be 1 billion. We're going to see, because these numbers are going to get quite large. So just remember, the room is about 0.1 megapascals, and you're going to see this in gigapascals soon. And we say that the enthalpy for pure elements is 0. But the most important reaction to all of this, probably in geoscience, if not for the planet, is that silicon and oxygen, silicon the metal, oxygen the gas, want to form SiO2, and they give off an enormous amount of energy when they do this. So this is quartz, silicon, is the stable product. It doesn't actually want to separate. If there's silicon and oxygen around, it wants to make quartz, and it wants to do it until one of these components runs out, because you're giving off a lot of heat when you do this. And this is now called the molar enthalpy of formation. Don't worry so much about this. And it is serves us quite well for silica. This is probably the single most important unit in geochemistry that we can think about. Entropy, people ultimately like to reference this stuff to entropy. I've tried to take this out because it's weird and non-intuitive and it doesn't make any sense unless you make these models, but I can't guarantee that I'll be able to do that for every talk. So people like to reference stuff to entropy rather than temperature. And basically, the entropy of every substance is 0 at 0 Kelvin. So people use that and basically just make an adjustment for the temperature. I don't like this. This is how people who do modeling of these really sort of high pressure, high temperature processes on a computer like to express the results because they find it more intuitive for them. I quite personally never understood the appeal, but I tried to get it out, and I've tried to put everything in terms of pressure and temperature because those are much more intuitive units. So we can actually use this to calculate the G of quartz. We know this was measured in the lab. Temperature we know, and the entropy is something that we can get by basically playing this game. So the important thing, and I've had questions, this is particularly because I've had a couple of questions about things at pressure. For example, last week someone came up and asked, where does the core start crystallizing? It's the middle rather than the outside, because even though the outside is nominally colder, the outer core is the liquid. Part of this is because there is both in the change in the Gibbs free energy, this quantity that we want to minimize, right? So this really wants to be a minimum. There's both a pressure term and a temperature term. So both the pressure and the temperature are going to become important for which phases are stable. So V here is the volume, S is the entropy. Entropy, again, is a configurational term. It has to do with how random the system is. And so we can use this to calculate G for any phase at any temperature and pressure by basically integrating. So by basically saying, we're going to start at the lab conditions that we know, change each one of these a little bit, note how much that changes G, and we're going to keep doing this until we get to our destination. So, G is what we're going to, G is the measure of how stable a phase is. It's only a relative measure. We're going to we can determine G basically by measuring these terms, or trying to measure them, and then we can calculate it at temperature and pressure mathematically if we know these terms here. How much the volume changes with pressure, which is the compressibility. So this is something that you can measure in a lab, and this is done a lot. People take a substance, put it under pressure, and see how much smaller the substance gets, how much more compressed it is. And then this is the heat capacity, and this is you heat a substance up, and basically how much energy does it take to increase by, 1 degree basically. So and then this is the heat capacity. So substances that have a high heat capacity tend to be really hard to heat up. Things with a low heat capacity tend to be really easy to heat up. So why have I been telling you all of this? Well, if we know G for various phases, we can determine which is the most stable. So this is going to be important if we have a molten planet and we want to have a model and make a prediction about what phase is going to crystallize first. The phase with the lowest Gibbs free energy is going to be the phase that wants to crystallize out of the possible phases that can crystallize. So this is something that we then have to determine, and then we can say, well, now I've got my molten planet. What do I want to crystallize? Which phase is it going to be? So we need basically all of this back work and determine this accurately for minerals up to pressures of hundreds of gigapascals. Right? The atmosphere is at 0.1 megapascal, so this is 100,000 megapascals, so basically 1,000,000 times the atmospheric pressure. We need to know what minerals are stable, up to thousands of degrees, 5,000, 6,000 degrees. Why is melt more stable than solids at high temperatures? We'll get into this in a second, because this is going to be really important, the reverse of this for magma oceans. What's stable diamond or graphite at 150 kilometers depth? This is where you're starting to get into diamond stability, so diamonds really are formed deep down. And this is one of the key questions that has not been solved. It's going to be critical to our efforts to understand what happens to our molten planet is how does pressure play a role in this? We can cool, we're going to drop in temperature, but pressure is also going to change our phase stability. Diamond instead of graphite. Pressure makes it much harder to melt a substance. So, if we have our sort of schematic, pressure and temperature, and we have some line at which this would be the line where you're melting, so we have a liquid and a solid, then does the liquid or the solid have a larger volume? Well, the liquid has a larger volume. It is less dense than the solid. So as you heat up, things expand. So the liquid is higher pressure favors low volume. So which phase is stable at high pressure? Well, at high pressure, you can see that the solid phase is much more stable. So that's good. And does the liquid or the solid have higher entropy? What do you think has more randomness, has more available configuration? Something that's really rigid, like a solid, where each atom has sort of got an assigned position, or a liquid, where all of these things, the bonds are much weaker, stuff can move around, right? The second one has got the higher entropy. So higher temperatures, where the entropy is important, is going to favor liquid. So we can see at higher pressure, we want to go towards the solid, and at higher temperatures, we want to go towards the liquid. So this actually tells us that this slope should be positive, a neat outcome, and that increased pressures is going to make it much harder to melt stuff. And this complicates our... so, at point A, what has the lower Gibbs free energy? The solid or the liquid? The solid, right? Because we're in the solid stability field. At point B, the liquid has the lower Gibbs free energy. So we've gone over some sort of a phase transition. We've gone over a crossover between the Gibbs free energy of the solid versus the liquid. So it's always the phase assemblage with the lowest G under any conditions that is the most stable. So as we go up, right, here's the equation for the change. So the Gibbs free energy of the phase versus temperature, it's going to go down. That's good. It's got a negative term. And now the question is, how does the liquid compare to this? Is the liquid going to have a steeper or a shallower change in Gibbs free energy with temperature? And the answer here is that it has a steeper one, because at some high temperature, you're going to have the melt, and it also has the greater entropy term. So the solid, because it is so rigidly configured, doesn't have that configurational freedom. So at some point, you're going to basically, as you heat up in temperature from A to B, you're going to have this crossover, and this is where the system starts melting, basically. Pressure has the exact opposite behavior. As you start to squeeze things, because the solid has the lower volume, it's going to want to become more stable. So if you keep temperature constant and just squeeze on a substance, you can actually get it to go from liquid to solid without doing any without doing any heating. Vice versa, if you have a solid at high pressure and you rapidly decompress it, you take it out very quickly, it's going to melt, because it is now too hot for its stability. So if you go basically from here in the pressure over, you might actually end up changing the relationship. This, by the way, is, if any of you use a pressure cooker, this is essentially the effect you're taking advantage of in the pressure cooker at home, is that as you heat up at pressure and atmosphere, so here's the known freezing point, so this is us here. As we heat up, we hit the boiling point at 100 C, and so we can only cook so fast. But the boiling path here, it comes up. So as you go up to higher and higher pressure, say with your pressure cooker, you can cook at higher and higher temperatures and still keep your liquid water. You're not going to boil it, so you can change the boiling point. Also, by baking instructions, if you're in Denver, Colorado, you need to bake stuff, you need to boil stuff longer, because the boiling temperature in Denver, Colorado is sufficiently lower that your pasta is going to take longer to cook, because you've gone the other way. You've gone down in pressure, so the boiling point comes down in temperature. So, what do we need to know in order to understand our magma oceans? How are we going to model a process that is taking place at, on this planet, from the surface down up to thousands of Kelvin, up to 300 gigapascal, so basically 3 million atmospheres of pressure. I think that conversion is right. We're going to need to know something about how viscous is a melt at those conditions. What is its density? What is its compressibility? What are all of these things? Right? If we're going to have a model for water, that's at sort of how water flows, and then as we cool the water, we're going to want to know at what temperature we start making ice in our water. This is the same thing, except it's applied at much higher temperatures and much higher pressure, so it's much more difficult to study. And so then, not only need to be able to describe these melts accurately in terms of their physical properties, but we also need to know what minerals are going to crystallize if I take the Earth, if I take the mantle of the Earth and melt it. What am I going to get first? Am I getting quartz? Am I getting olivine? Am I getting a pyroxene? Am I getting a plagioclase? You have all of these minerals on the back of today's handout, in case you're curious, in case you don't know what they are. So what phases am I going to get? What's going to crystallize first? And how does that depend on pressure? So that's going to depend in part upon this should actually say liquidus, not solidus. You have the definition. So the liquidus is the temperature at which you first start to get crystals in a melt. The solidus is the temperature at which you have no more melt left, at which it's 100% crystalline. So sorry, that should say liquidus. And then what's the density, compressibility, etc. of the phases that crystallize? Because that will determine how our magma ocean evolves as these phases start crystallizing. What elements am I taking out of the magma? How does the molten portion evolve chemically? If I take out, say, olivine, that has got a lot of magnesium and iron, I'm going to have less magnesium and iron in the melt. And that's going to have huge effects on densities and if stuff goes up or down. So, in order to do these experiments, because this is not actually trivial, in order to get especially down to the lower mantle pressures, you need an apparatus called a diamond anvil cell. These are fantastic things. This is about 2 inches in diameter by 1 inch, and this is the entire apparatus. And what this is diamond is a really hard thing, and it's clear. So you can shine X-rays through it, you can make other measurements, you can shine lasers in through the diamond to heat your sample. So we're going to have, so this outer portion here is basically the seed. In here, I hope you can see, is the diamond, and in the middle between these two diamonds, here shown in the really tiny, that's the sample. So these samples might be 100 microns across, they might be 20 microns across. Human hair is somewhere around the order of 20 microns, so these are samples that are, you know, a little bit bigger than your hair is wide. And then, in order to generate the pressure, you basically turn the screws to push the diamonds closer together, and you're going to shine in laser light in order to heat the sample. So you can shine in really concentrated laser, and you can get up to temperatures 5,000 to 6,000 Kelvin. Some of the highest pressures achieved here, sort of 200-ish GPa. These really get you into the lower mantle. These get us pretty close to the core mantle boundary. But we only get a tiny amount of material to do this with. So there's, again, basically every time you do this at these high, you need to replace your diamonds. So this is, there's some consumable costs here. There's a couple of things you can then do. I mean, we haven't actually done anything useful yet, right? The ability to take my sample, put it in a diamond Anvil cell, get it to pressure and temperature, we haven't learned anything yet, right? We haven't yet gotten any useful information out of this. So there's a couple of things you can do. You can do this and say, well, I've heated my sample and I've made melt and I'm going to study the chemistry, so I'm just going to cool it and recover the sample. We'll talk about that next. That's probably the easiest to understand. And for this purpose, this is one of the most important. It's how we get elemental behavior in these conditions. So the other one is that you can, for example, shine through a beam of X-rays. So now you've got to take this thing, go to a synchrotron, where they fly electrons in a circle and make X-rays for you. And then you've got to take this entire apparatus, align it so that your X-ray beam goes through your tiny sample while you've got two lasers shining at it. And then you've got to collect the X-rays and use those to do something useful. So the most common experiments are diffraction experiments. The X-ray is going to interact with the solid material in the sample and be scattered by characteristic amounts depending upon the interatomic spacing, basically. So this can tell us something about the crystal structure. So this is how you then learn. You then take that data and you say, well, these atoms are so and so far apart. What structure does that look like? And so what's the atomic arrangement? You still need computer models to interpret this. But the impression that I hope you're getting is that this is not a trivial effort by any means, and that these are some really impressive experiments that are being done where people are taking these tiny cells, right? This is the entire thing. The diamond seed in here is this small hole in this kind of a setup, shining X-rays through it at $1 billion-ish facility, using lasers to heat the sample up, also that we can try and get basically a single data point, because this lets you put in one experimental composition. So once you take, in the case of the chemical compositions, once you take the sample out, you've put it in your diamond Anvil cell, you've heated it, you've gotten it up to pressure, you take it out, you can then do, to understand the chemistry of it, you can use, here in this case, an electron probe, so you can generate a beam of electrons, shoot it at, and so here is the sort of simplified picture of an atom. There's our nucleus, here are our electron orbitals, really classic outdated picture, but it works. And we're basically, and the electron beam that comes in is going to take and kick off an electron from the atoms as they're sitting in the sample. And then another electron is going to go, oh, look, there's a free spot in a lower orbital, in a lower energy. I want to go there. And it's going to emit an X-ray. These X-rays are then characteristic based upon the energy levels of the K, L, and M shells, so of these electron transitions. And then you can collect these X-rays and measure their energy by having a detector that is either energy sensitive or, in a more complicated case, that is wavelength sensitive. But for now, just focus on the energy. So here is the energy of the X-rays as you shoot at a sample. So there's iron, there's the K alpha line. So this is, if you kick out something out of the K, this is a nice line. There's oxygen at much lower energies, there's silicon. So you can use this, and the peak heights can tell you something about how much there is. So basically in this sample, there's more oxygen than there's iron. There's quite a bit of carbon, although really hard to measure by this technique. And then there's a little bit of silicon. You can see some phosphorus, sulfur, some calcium. There's a little bit of magnesium identified. So you can use all of this to try and understand what the chemistry is of the elements that you have in your sample. So here is here's an example of what these end up looking like, and so you can get the spatial scale. So this is from Bethany Chidester. She was here in Chicago, defended her PhD recently, working with Andy Campbell. They did diamond anvil cell experiments. So they took, and what they did is they took a rock powder that looks very much so like the mantle. So they tried to make a chemical analog, and they plopped in some metal, and then they put in some uranium. They wanted to know if uranium would go into the Earth's core or not under formation. So they did these experiments, and here, this is the unmelted starting material. This is a 2-micron scale bar. So this is now incredibly tiny spatial scales. And then here you're starting to see, here's some of the stuff that's been heated. This is the metal blob. But actually, this outer portion isn't yet the melt. This is a phase called perovskite. The melted portion that you're trying to analyze is this here. So you're trying to find and figure out how much uranium is in the sort of green ring versus the blue versus the iron. So these here are individual X-ray maps using this technique. So you basically go across the sample and say, how many X-rays for oxygen am I getting at each spot? How many of aluminum, magnesium, uranium, iron, silicon? And then this is just a sort of a composite picture, so you can see that in this ring out here, there's a lot of uranium, and there's hardly any uranium that's gone in the metal, so uranium does not want to go in the core. But this is then one of these experiments, and you've got to basically do a whole lot of these experiments in order to figure out what happens at different pressures and temperatures, and each one is quite a bit of work. So this basically then will provide us one tiny piece of this information towards trying to understand what the thermodynamics are of these what the chemical behaviors, what the physical behaviors of these elements at high pressures and temperatures. This was done 60 GPa. It's about mid-mantle and very high temperature, sort of 5,000 degrees. It is also, if you notice, really hard to actually know your temperature, right? Here is the blob of iron. Here's the melt. This is unmelted material. So you have enormous temperature gradients within these that are really challenging to deal with and make this work quite a bit harder. So then you ultimately get each experiment represents one data point. So here's the temperature of the experiment in Kelvin. So for intensive purposes, up when you're this high, this is the same as Celsius. You can just take 300 degrees off, you'll find you're at the same. And this is the log of the distribution coefficient between iron and the silicate melt. So this is basically how much uranium divided is in the silicate divided by how much iron is in the metal divided by how much uranium is in the metal divided by how much uranium is in the glass, that silicate, that melt. And then you take the log of it. So this is basically saying that there's 1,000 times more uranium in the mantle than there would be in the core if they formed at these conditions. And these are her experimental points. Here's some other people's work that say it's even less likely to happen at lower temperatures. So as you get up, it does seem more likely, but it's still, basically 1 out of 1,000 uranium atoms is going to try and go into the core. So not really important, but still important. The other techniques that people can use, and I wasn't joking, is that there's a really easy way to get high pressures and temperatures. You shoot a gun at it. So this is actually part of my PhD. These pictures are taken at the Caltech Shockwave Lab by myself. And this is a gun here. You end up loading what's going to be used as the bullet down here. And then at the end of the barrel of the gun, you screw on your sample that's got your rock in it that you're going to shock. So there it is. Screwed on prior to the experiment. These two lasers are these red laser lights here are to measure how fast the projectile is going right before it hits, so that you can try and understand something about the pressure. And there is the projectile. So here is a tantalum plate mounted on some plastic. This is going to get shoved in. This bottom ring here is going to break off, and the gunpowder gets loaded behind this to shoot this at the rock. They have a fun room that's got all of these labels on it. They have quite a bit of gunpowder. They actually, interestingly enough, they use pistol powder, not rifle powder or anything. They found that the gunpowder used for pistols is the most interesting, gives the best performance. So this is stuff that you can buy in a sporting goods store that'll sell you a gun. And actually, our experiments were delayed because stores didn't have enough of it. This was around the second election of Obama, and gun sales tend to go up. So scientific work was delayed by people being paranoid about having their guns taken away. So this is what that thing I showed you after. This is what it looks like after this was flat. You're making a crater, and this is the rock. So this is a 5 millimeter scale bar. So it's about 5 millimeters, really thin. This used to be a flat piece of metal, and that indentation we've cut off part of it, but this indentation used to continue. We've basically made a crater in it because we've shot something at it. So this went up, and this experiment only went up to about 18 GPa. So this is still somewhere in the upper mantle. We haven't even yet gone down to mid or lower mantle type pressures with this, and you're already doing a lot of damage with it. The technical details of how you get something then useful out of these are far beyond the scope, and I'm not entirely qualified to talk about them anyway. We'd need probably Paul Asma or somebody to come talk about this. But people can also make these measurements in situ, where they actually don't have the metal. They actually shoot directly at the rock, and it vaporizes. And in the split second where the shock wave is there, they can make useful measurements about the behavior of the material in the shocked state. So this was a recovery experiment where we got it back. We ultimately dug the rock out of the stainless steel and did some analyses on it. But just to give you a flavor of how much work goes into this, because we haven't yet talked about magma oceans, because this entire setup is there to tell you that while there are really nice models, probably none of them are close to reality, because there is not anywhere near enough of that work that I've spent the first part of the lecture talking about that has happened, because some of it is frankly quite boring. It's not a lot of fun to say, today we're going to shoot this composition to that pressure and temperature and kind of do this systematically to fill this out. You'll get bored. And there's just an awful lot of this work to do. So people have come up with these models, but we'll get to the sort of punchline. The range is you can almost do anything you want in these models, and that in the future lectures with the geologic record, one of the things that we want to understand is how these processes actually work in nature, because the lab experiments are still hopelessly under constraint. So,
the shock wave your image, that's the image asteroid impact? Or?
That's the image I showed the sample. That's after we dug it back out and cut it in half with a bandsaw.
Was to represent an asteroid impact or something?
It was to represent an asteroid impact, yes. So that sample was not trying to understand these conditions sort of in the mantle. That was actually to see what happens to samples during an asteroid impact into a surface.
Part of the broader model of how the mantle core would form. All the different things
Close.
that we do.
Close. We'll get back to this much later. It's about how we try and date impact events. So the details, that experiment was conducted for a totally different reason, but it is the same technique that they used to do this work. So I thought I'd show some pictures that I had taken, because they don't put a lot of these pictures. I was trying to find some, and I emailed some people who do this, and there's not a lot of pictures. They tend to give you PowerPoint presentations with graphs and data and stuff rather than pictures of their setup.
Shooting marks and things is pretty cool.
They actually, one of that's the smallest gun at Caltech. One of the middle-sized gun is a World War II howitzer. And the bigger gun is, even bigger. So in the accretion scenario, right, you have planetesimals that are going to hit together. And here, basically, the color scheme is right. You've got a sort of a core, a mantle, and a magma. So core, mantle, magma, you might, after impacts, have, some localized magma here. It might be molten in the middle. As these things are coming together, there's a lot of impact. There's a lot of energy being released. If you have impact, you might have these sort of magma ponds. But that by the time you make something planetary scale or even the size of the moon, you're more or less guaranteed to melt the outer portion of an object, possibly all the way down to the core. And that how this crystallization happens is what we're going to try and understand. So these models, if you make different sized bodies are going to behave very differently for this. It's just one of the great complications to this is that this is simply depth in kilometers here. So these are all down to 500 kilometers. These are the temperatures are 1200 to 1800. So we're really only looking at the outer part of, say, the Earth when we do this. The moon, you go quite a bit deeper in. But because the moon is so much smaller, by the time you're at 500 kilometers, you're only at 2.5 GPa. So you're still actually relatively low pressures, whereas on Earth at 500 kilometers, you're at 15 GPa. So you've got a much higher pressure to deal with for the same depth. And these curves here are the liquidus and then the solidus. So this is when the onset of crystallization, this is when it's completed. And this curve in purple here is an adiabat. And the adiabat is the line, as you go down in pressure, this is basically a line of constant temperature, except that you won't have constant temperature because pressure, as you squeeze something, it warms up, it gets hotter. So who here has been to LA or heard of the Santa Ana winds? These are winds that come off the mountains. There's an air mass sitting there, and as they come and fall off the mountains, they get compressed and heat up. So you get these hot, dry winds, and that's the point. So the adiabatic process, the adiabat, is one where you have no heat flow happening between things. So in a situation like the moon, where you've got really no change in pressure, it's just a line along the same temperature. As you get to a planet like the Earth, you're going to have some features. So this is going to have a slope where you're going to have higher temperatures at lower depths, even though there's no heat. So these are the sort of where they're sort of in a thermal equilibrium, and you just have this temperature gradient because of this pressure effect. So it is basically, it's just accounting for temperature changes as you're increasing the pressure. So it's basically the closest you can get to a sort of a straight same temperature curve as a function of depth. So to go back to this, you can kind of see this on the moon. This is basically as you take sort of one temperature slice. And this is important because magma oceans are thought to convect. So as you're boiling your water, you have convection really tries to get and equal out the temperature everywhere. So in convection, as you heat something up, it is going to become less dense and it wants to float up. So as you have stuff happening, as you're cooling on the surface, you're going to make material that is colder, it's going to become denser, it's going to want to sink. Stuff at the bottom is hotter, and so it's less dense, and so it wants to float. And this is happening, and this is going to try and get everything to the same temperature. So this is why the adiabat lines are drawn rather than some other lines. This is what convection is trying to do. So this is really what your magma ocean is trying to do, because your magma ocean is most definitely going to convect, and that makes this problem so much harder. So on the moon, you can see that because of the pressure not changing as much, the liquidus and the solidus, basically, you can get, it's a lot easier to get melt at depth, whereas on the Earth, because of the increasing pressure, it's much harder to maintain a magma ocean down to deeper, down to the lower depths. So this means that the crystallizations, and the adiabat, basically, as it's cooling, it's moving from right to left. So wherever you want to start it off, it's arbitrary, so it would have been here. So the magma ocean would have crystallized from the bottom up, is the point of this. Because you're crossing in pressure space, even though it's hotter down here, the higher pressure is really, the magma ocean is going to try and crystallize from the bottom up, is the argument. And then to put the model in a slightly different scale, so basically on the moon, you'll have 100% liquid in the outer 150 in this example. Then you have very little crystallinity even at depth. On Mars, which is sort of intermediate, you'll have less being 100% liquid. And by the time you get to Earth, at least in this model run, and for these conditions, it's really hard to maintain melt below 300 kilometers depth. So you're going to have this process, and that therefore modeling this on the moon is actually much easier because you don't really need to worry about the pressure as much, whereas modeling this on Earth is much harder because you need to worry about the pressure component. So this, what these models then do is they say, well, as I cool my planet, without considering the convection, without considering the motion of material, I'm going to cool the planet along an adiabat. So I'm going to try and cool it is pretending there's convection, but without having to model the convection. That's what these models do. This is still the Elkins 10 work. You're going to make post-perovskite magnesium, iron, silicon, magnesium, iron, silicon, magnesium, iron. So you're making phases that if you go, especially for the mantle, these look really nice and reasonable for mantle, but look at the crust. You're making, in the outer part here, given as pressure, but really it should be given as a depth would be more useful. But this here, this outer part, this is the crust. And if you look on the back of today's handout, where you have the chart of sort of what rocks are called versus the minerals coming in, the one that's hard to read, I'm sorry, is pyroxene. So you're making something that is quite mafic, right? You're making something that looks like a basalt, right? You're making plagioclase, pyroxene, olivine. So this is telling you that the surface of the Earth, according to these magma ocean models, is going to be something that looks an awful lot like basalt. But these models are highly simplistic, and that's what the part we're going to finish up on is they don't simultaneously simulate the dynamics, the convection, and the chemistry. These models say, I know how the temperature evolves from convection, but I'm going to leave out that messy part where it moves material, and I'm just going to crystallize it as it's happening. And then at the end, I'm going to turn on dynamics because whatever I make out of that process is not actually gravitationally stable. They concentrate really dense stuff at the surface, and then they say, well, now we can turn on the convection, and boom, the entire system overturns, and my crust is going to try and sink into the lower mantle. That's not right. That's not how this works. You have to simulate the chemistry and the convection at the same time, and that, independent of not having enough of the constraints for this modeling, we don't have the computational power for that quite yet. So these models are sort of highly simplified, and so I would argue that while they're a useful guide, a useful thing to think about, that you're going to crystallize from the bottom up, that the pressure effect is important. You're probably going to make magnesium, iron, silicon type minerals, something like olivine, perovskite, etc. for the mantle. This is all great, but they're not exactly great approximations to what happens in nature. Because convection really messes with you, because whether or not a crystal stays entrained in the flow, right? If you imagine having a river, if you've seen the muddy river, right? There's particles suspended in the river. At some point, if those particles are too big, they'll just settle out. So if you have your river, you don't tend to see big rocks floating down in your muddy river, but you see small particles. So as minerals nucleate, such as here, and form, at some point, they're going to reach a critical size. So this is grain diameter in centimeters versus heat flow. Just ignore the labels, but what I want you to notice is that depending upon the gravity, the strength of the gravity, planetesimal being low, stuff has to get up above a certain size in order for it to settle out of this convective flow. If it's below that, it's just going to flow along with it, and it's not going to actually chemically separate. It's just going to go along, and it might even go up and hit a lower pressure regime where it melts again. Or it might settle out, or if it's not a dense mineral, if it's lighter than the magma, it might float to the surface. This is what we think happened on the moon, where plagioclase is crystallizing and floated up to the surface and gives us the anorthosite layer, the white crust on the moon. So, the simple model, as I've argued, is making plagioclase, pyroxene, olivine. This is basalt, gabbro, whatever you want to call it. This is something mafic. The continental crust, by the way, is granite diorite, is up over here at sort of 60 to 70 weight% silica. So these models don't actually give us a way to go from here to over here. So we're going to need some other process to make the continental crust. But if the magma ocean makes something closer to this in composition, we don't need a process for generating the continental crust. This is what we'll get into next lecture, is that whatever the outcome of this state is, it's the starting point for any thinking about the crust. So we can say, well, people have proposed this. Paul Warren did this in the late 80s and said, well, instead of using one of these models, we can look at the moon, right? This white stuff here is the anorthosite layer. This is the flotation crust. So there's the lunar magma ocean. Olivine and pyroxene are sinking to form the mantle. Plagioclase floats, accumulates at the surface, and we can go pick up this plagioclase. In fact, the Apollo astronauts did just that. And then we have a crust that is plagioclase. So if I go back, we've already sort of moved ourselves into this. So we've moved up to a better portion to be in, closer to continental crust. The criticism of that is that water, so plagioclase is only a little bit less dense than your magma ocean, and water really changes the density of magma. So people have argued that here's the plagioclase density, here is 1 GPa, and here's 1 atmosphere, so this is the density of the magma, and this is how much water you put in it. So if you have, 5 weight% water, which is way too much, your plagioclase is denser than your magma, it's going to sink. But for anything reasonable, sort of 1 or so and below, especially as you have even a little bit of pressure, the magma is going to be denser than the plagioclase, so the plagioclase can float. But the criticism of this then is, can you make the plagioclase large enough to decouple it from that convective flow, because the convection is happening at really fast speeds, and so you actually need a fairly big plagioclase grain to be able to say, nope, I'm going to float up to the surface rather than get dragged down with the convective currents and be melted again. We have no idea if this can happen on Earth. We weren't there. There's another model that this is probably the closest to my favorite idea, and it's the one that we'll finish up with, is that as you're making, so here is your magma ocean and you're convecting, so here's the stuff coming up, here's the stuff coming down. As you are convecting, you're making the olivine at the bottom, the pyroxene, this is, let's just go with olivine for now. This is also, as this crystallizes, if you look at the back, you'll see this will suck the melt out of magnesium and iron, and it can make a light. The layer above it from which it's crystallizing is going to have less magnesium and iron. It's going to have more of the aluminum, sodium, calcium, sort of silicon, the stuff that you need to make plagioclase, that you need to make this, this sort of crust. But instead of floating the crystals, what if you simply floated that molten rock, popped it up to the surface, and then it's going to crystallize as it hits the surface? So rather than saying we need to decouple the crystallizing plagioclase, we're just going to take this melt that is forming in front of the crystallization front. So this is the magma ocean solidifying, going up in this direction. As you're making, the olivine that's crystallizing is dropping out, the melt that it's crystallizing from is depleted in these, is much less dense, and can come up into convective currents and float up and maybe give you a crust that is rich in things like aluminum, silicon, sodium, potassium, calcium, and that this might be a way to make a crust. This has not really been picked up upon. This is 1987. The models haven't done that much, and this is the sort of chief criticism of these simple models is that the models such as what the Elkins tent and stuff, where I showed you the adiabats and such in the crystallization phase, they can't model this process because they don't do the convection. So this is at the scale of, somebody sketched this on a piece of paper and proposed what if this process, and the computer modeling 30 years later has not yet caught up to really allow you to do this. So we still need to look at the geologic record for what happens. So we need a record, because these models, we can see the entire range, right? We can make something that is really felsic, it's got a lot of quartz and plagioclase in the Morse model, to something that's making you a basalt, are all things that have been proposed for this, and it's in part because of how hard this problem is that we don't actually have a good answer. So let's go, next week is the first lecture where we'll really start to look at the terrestrial geologic record to try and understand what it tells us about these early events. Thank you. Questions? Yes?
Our process, that happen around the time of the supernova, or is that like billions of years after?
That's going to happen. That's going to happen during. So as the supernova explodes, you've got a lot of neutrons, basically. So that is going to happen, and this is a really quick process. So the R process, the neutrons will come through. It's kind of a one-time thing. You're basically shooting a lot of neutrons through. You're going to make these really unstable elements, and then they're going to decay back towards stability. So
heavy elements like gold.
That's a great way to make them. They will also be made during the S process as well. Because you can sort of slowly work your way up until about you run out at lead 210, because that is unstable and will decay back to bismuth. Other questions? Yes?
It seems to me that you're saying that you ignore the convection because the pressure sort of locks things up. The convection is going to isothermalize things. So as long as you don't thermalize things, you adiabatic. the processes are adiabatic. So you're assuming it's adiabatic and making the structure, and then you do iterations on it and all these models that go convex. But you're not doing both at the same time. You're doing a good model.
That's my point. Yes. So
Okay, say because these things are chaotic and Bernard cells and all that.
exactly. So these are really complicated, and the reason the last two are sort of sketch models because we can't actually simulate them.
It's
The models. So those are the ones that are basically having thought experiments. They're saying, well, this is then going to be less dense, right? I know I'm going to drop out olivine. It's the first thing that's going to crystallize. So I'm going to have a layer that is less dense, and then I'm going to have a convection. Well, in a convective situation, that might even drive the convection, or it might be a big term in driving it. So the paper comes up with compositional convection, where it's saying that I'm now making this not very dense melt layer above where I'm dropping out my olivine. That's going to want to float. So even if it wasn't convecting, that might start the convection. So then you've got this, and then now you've got a great way to generate a sort of proto-continental crust, because you've got this light, this melt, and you've got a way to get it up to the surface because it's less dense, it wants to come up. So my criticism of the sort of the alkenes Tanton stuff, and the reason that I didn't spend the entire lecture going, look how cool we can make all of this stuff, and these computer models say this, is because they don't do convection and crystallization and that chemistry at the same time. They basically alternate. So they use a thermal profile for the planet and the cooling profile that assumes convection is happening, but themselves don't calculate the dynamics.
So this depends on the time scale. If your convection is slow enough, these models should work. But they're telling they're not slow enough on the time scale.
The simple calculations, you're talking kilometer per second flow rates or something. It's really fast convection.
No, okay. That slows it away.
Yeah, but the high convection rates are easy to predict, but they're very hard to numerically model. We still have a problem. Mantle, even with the solid, getting the solid to convect, which is a lot slower, right? The mantle is convecting, even though it's solid.
But that's why high pressure is a consideration.
High pressure is a
consideration.
high pressure is a consideration because the pressure goes into what is crystallizing, what phase assemblage is stable.
Slows it down.
Yeah, so it will change the behavior of, it'll change at what temperature you start to get minerals, what phase of the mineral you get, how much of the magnesium and iron and silicon you're sort of sucking out of the melt by crystallizing stuff. So the pressure makes this more complicated because we can't just say at the surface of the Earth, I crystallize from this amount of composition, I'm going to get olivine. Well, olivine's not the preferred phase down there. It actually goes to something called post-perovskite. Because it's getting much more compressed. So you actually need all of that data because you need the densities, right? If you're going to think about convection, density gradients, density differences are really important. So you need to know, because olivine is going to have some compression behavior, but if it goes to a different phase, you can't use the olivine as a model for what's happening down there. So you need to actually then generate those conditions in a lab to get this. And this work is really, this is difficult. These types of the diamond anvil cell experiments that I showed with this really small melt layer that's less than, a micron, it hasn't been long that we've been able to do useful analytical work on this for the composition. That's maybe, call it 15 years ago, people started to be able, or maybe 20 years ago, people started to be able to do this, right? You did this in the absence of a lot of the advanced analytical techniques, then you can't get any useful information out. So there's a huge technological challenge here as well. Yes?
So how far are we away from being able to do the kind of simulation that you would like to do?
That is a really good question. I'm probably the wrong person to answer this. And I'd say we're a really good bit off because people are arguing some of the really basic material properties are still argued about. For example, what's the melting temperature of iron at 300 GPa? Easy question. There is a huge disagreement in the literature because it turns out in these diamond anvil cell experiments, it's really hard to define how you define melting, right? Water, in the bottle example, it's really easy. It flows, right? It takes the shape of its container. That's really easy. In these experiments, what they do to figure out just simple iron, what temperature it melts at, they take it and they do the X-ray diffraction, and they say, here are the iron peaks, and they're going to go incrementally to higher and higher temperatures, and at some point those peaks are going to disappear. But that's not going to happen sharply. And that transition itself will introduce some slight pressure changes. How well your experimental setup is calibrated, right? Basically, your experimental setup at 300 GPa and yours over there might not agree because the calibrations, these things need to be calibrated. So there is actually a huge debate in literature. We'll get into this a little bit. This makes, for the thermal conductivity, which is another huge parameter to this, it's also debated heavily, makes huge differences to how easy it is to have a magnetic field, how easy it is to have a dynamo. We'll get into that in the future, but there are debates about really basic material questions. So it's a question of computing power. The computers need to get faster, and the graphics cards. So it used to be that you needed a processor to run a lot of these models, but people are starting to go and use graphics cards for these heavy mathematical calculations. This is really cool, and it's really moved that along and made it much easier, much cheaper to get a really fast computer. So I don't know what a good answer is, but some of that were away from simply on a computational front of needing the computing speed to continue to increase. And some of it is there's a lot of basic material properties that need to be worked out, that need to be measured, and that's going to take some really challenging experimental and analytical work to try and do. So I don't have a good answer, but I don't think it's anytime soon. Yes?
Will you cover in a future lecture the transition between space dust, planetesimals, protoplanets, and then planets? I mean, a reference of mass for the different categories, or could you give a quick answer now?
Planetesimals, you're sort of thinking the 100-kilometer scale. Dust, you're really thinking the sort of millimeter type scale, and then there's a sort of the size distribution in between. So by planetesimal, think an object like, think the asteroids sort of out. Think, 100-kilometer type objects. And then these are going to sort of come together. But as the solar system is forming, you're seeing sort of a continuum in sizes, and they're just going to gradually get larger. You're going to work your way up to millimeter-sized object, meter-sized objects, and then to a kilometer or 10, 100-kilometer objects. And those are, when I say planetesimal, really what I mean.
Yeah. Would it be possible under the right conditions for the magma ocean to actually boil? Like if there were a sudden heating by impact?
Yes. The one example where this has been proposed, this is a really recent idea that people are still sort of playing with, that the moon forming impact would do this. So you have the impact, and what you're actually making is a sort of silicate gas that is really hot, 5,000 to 6,000 degrees type hot, and that's going to condense out and form stuff. So that those types of ideas are being talked about, but they would require a really extreme event, because the natural thing, if you have the molten rock, the natural thing to do, it doesn't want to be in a vapor phase. It's really hard to do that. It wants to form a sort of a chill crust. So the outer part, if you put the magma, if you've seen like YouTube videos of lava lakes, or if you've seen lava lakes, they form this sort of very thin sort of black crust. That's minerals starting to crystallize, and that's basically because it's radiating to space, and it's such a huge temperature gradient that it cools really quickly, and then forms a really thin, not very stable lid on it. And so that stuff is also going to affect how this evolution happens. So I didn't even talk about coupling the magma ocean to the atmosphere and to other things, because if you, say, have a lot of steam, that is a great insulator. So if you have a lot of, say, water that is exsolving from your magma ocean, it makes a steam atmosphere. That means that the surface of your magma ocean is going to be really hot. It's going to be kind of insulated. If you don't have that, you're radiating to space, then you've got a great way to lose a lot of heat, because you're just going to lose it by radiation to space, and you're going to form these lids that are probably going to sink when impacts happen, and they're going to be unstable. So that's going to really also is a factor. So you can't just even do the convection and the cooling. You've got to also think about the heat loss is the heat going into space, and you've got to see, is there a giant layer in between or not?
Yeah, you made a reference to diamond. Diamond, of course, is formed under these enormous pressures and temperatures. Is it possible, given enough time in the future, that diamond will someday revert back to a more stable, different configuration?
If you take it out? If you take it out?
Diamonds, diamonds are forever. Well, are they really?
There is some rate at which it happens. At room temperature and pressure, this is negligible. So it's possible, but not on any human lifetime.
Oh,
Well, in summary, it sounds like we keep bumping into this. It sounds like we just don't know because the models are so enormously complex, and also we don't have the experimental data as to how materials function under high pressure and temperature, and it's going to take a huge amount of work to collect the information that we need. So we have to estimate what the early Earth looked like by looking at actual geological samples on the surface.
And that's
as opposed to using models, because models will just take too long to figure out.
Yes, that is, I would say, a really good summary of the first sort of part of this that I've tried to do, because some of the background, the reason for starting from the modeling perspective and from this sort of, well, what would you do in the absence of a geologic record, is because it's exactly thinking along these lines that came up with the early Earth was hellish, dry, and hot, and that, you didn't have any water, or there was molten rock on the surface. It was exactly this type of thinking in the absence of a geologic record that led people in this direction. So I wanted to start from that basis of simply how enormously complex and difficult this is as a task, to say that having your intuition and saying, oh, the planet formed, it was hot, so that, for a few 100 million years it was hot and hellish, it's not a really solidly based guess.
It's a guess based on models that are too complicated to really be useful.
Yes.
We went to the models because we didn't have the geological evidence, because there's been so much erosion and change that we don't have the samples that we need.
Yep, and that this is modeling sort of in the absence of evidence, and that we actually have the evidence and we're capable of analyzing it. And what I want to spend on now is, what does this evidence tell us? And let's, put aside some of the sort of the more model-based stuff and go look at the geologic record and see what it tells us when certain events happen and about certain things that happen. And then it would be great if we could then take this evidence and build new models on it, but that step is not quite yet being taken. So we're going to have to take the evidence-based view from the geologic record for what it is, for what happened when.